Welcome to AI Frontiers, where we explore cutting-edge research shaping our technological landscape. Today we're examining the robotics resilience revolution, the fundamental shift from fragile machines to systems capable of graceful failure. We've analyzed 48 cutting-edge robotics papers focusing on safety, adaptation, and real-world deployment, with a breakthrough discovery that robots are learning to fail gracefully. This November 23, 2025 research compilation reveals how modern robotics is moving beyond traditional approaches to embrace resilience and adaptability. Picture this scenario. A robot falls down, and instead of breaking into expensive pieces, it tucks and rolls like a trained martial artist. The robot strategically protects its most vulnerable components while absorbing impact with reinforced body parts designed for damage resistance. This represents a fundamental shift from failure prevention to graceful degradation, teaching machines not just how to succeed, but how to fail safely. This isn't science fiction anymore. It's today's reality in advanced robotics research, where systems are designed to handle the inevitable, rather than pretend it won't happen. These advances represent far more than incremental progress. We're witnessing fundamental breakthroughs that could transform robotics entirely. Humanoid robots now coordinate their entire bodies like professional dancers, with every joint working in perfect harmony. Tiny drones weighing less than paperclips perform complex aerial maneuvers. Robots learn sophisticated behaviors simply by watching humans demonstrate tasks. Perhaps most remarkably, systems can now understand plain English commands and translate them directly into complex physical actions, making robotics accessible to anyone, regardless of programming expertise. Think of robotics research as the ultimate interdisciplinary orchestra, where multiple fields combine to create technological symphony. Computer science provides the conductor, algorithms and intelligence that coordinate everything seamlessly. Mechanical engineering supplies the instruments, physical structures, joints, and mechanisms that enable movement. Electrical engineering powers the entire performance through sophisticated sensors and precision actuators. Artificial intelligence serves as the musical score itself, encoding the patterns and behaviors that bring the whole system to life. The unique challenge is that this orchestra must perform live in unpredictable venues, with no pause button when things go wrong. Our first major research theme focuses on whole-body harmony. Imagine trying to pat your head while rubbing your stomach while walking on a tightrope. Traditional robotic systems treat these as separate, independent problems requiring individual solutions. However, cutting-edge research is creating systems where every joint, every motor, and every degree of freedom works in perfect coordination toward common goals. This isn't merely about making robots more capable. It's about fundamentally reimagining how machines can embody intelligence through their complete physical form, treating the entire body as a unified, intelligent system. The second theme explores multi-agent coordination, drawing inspiration from natural phenomena like flocks of birds wheeling through the sky. Each individual bird follows simple local rules, yet together they create complex, beautiful patterns that seem choreographed. Researchers are developing algorithms that enable multiple robots to share information seamlessly, coordinate their movements precisely, and achieve goals that no single robot could accomplish independently. Whether it's swarm drones conducting search and rescue operations or autonomous vehicle fleets navigating complex intersections, this research establishes foundations for collaborative robot ecosystems. Theme 3 represents perhaps the most transformative advancement: vision-language-action integration. Imagine explaining to a friend how to make a sandwich. They understand not just your words, but can see what you're pointing at and translate that understanding directly into coordinated hand movements. This represents a fundamental shift from robots requiring specialized programming languages to systems that comprehend natural human communication. Instead of needing expert programmers to modify robot behavior, we're approaching a world where anyone can simply tell a robot what they want accomplished and watch it happen. The breakthrough findings emerging from this research are truly remarkable and game-changing. Researchers achieved 80 Hz full-body inverse dynamics control on real hardware, meaning robots can recalculate optimal forces for every joint 80 times per second while maintaining perfect balance. A library robot improved its book identification accuracy from 32% to 72% through continuous learning during deployment. Most impressively, multi-robot systems achieved 100% collision avoidance across 100 randomized trials. Additionally, robots are now discovering unique movement styles, trotting, galloping, jumping, even handstand balancing, through pure optimization rather than pre-programmed patterns. Today's featured paper comes from Ziyu Meng and colleagues, addressing one of robotics' most practical yet overlooked challenges: SafeFall, learning protective control for humanoid robots. This research tackles the inevitable reality that even sophisticated robots will sometimes lose their balance and fall. Humanoid robots represent some of the most expensive machines ever built, often costing hundreds of thousands of dollars. A single fall can cause catastrophic damage to delicate sensors, precision actuators, and structural components. Rather than fighting this reality, the researchers embraced it, asking how robots can fall safely when the inevitable happens. The SafeFall system represents a masterpiece of engineering psychology applied to robotics, consisting of two interconnected components working in perfect harmony. The first component is a fall predictor, a lightweight neural network that continuously monitors the robot's state, distinguishing between recoverable disturbances and truly unavoidable falls. The second component employs reinforcement learning specifically for damage mitigation rather than fall prevention. The system learned to protect vulnerable components strategically while absorbing impact energy with robust body parts, developing martial arts-inspired protective maneuvers through comprehensive simulation training that modeled both robot dynamics and potential component damage. The experimental validation on a full-scale Unitree G1 humanoid robot demonstrated extraordinary effectiveness that exceeded all expectations. The system achieved a remarkable 68% reduction in peak contact forces, directly translating to reduced stress on mechanical components. Peak joint torques were reduced by over 78%, protecting expensive actuators from potentially damaging overload conditions. Most remarkably, the system eliminated 99% of collisions with vulnerable components, effectively creating an invisible protective shield around the robot's most critical parts. This enables aggressive experimentation and real-world deployment without constant fear of catastrophic damage. Looking toward the future, these advances point towards revolutionary robot ecosystems, much like the Internet's evolution from a nuclear attack-resistant network to the foundation for social media and e-commerce. Robots are transitioning from specialized tools to general-purpose partners capable of understanding natural language, coordinating with other systems, and learning from experience. We're seeing the emergence of interconnected robot networks that share collective intelligence and solve problems beyond individual capability. These distributed systems could revolutionize smart cities and space exploration, while foundation models serve as physical interfaces to vast encoded knowledge, enabling robots to explain their reasoning and suggest alternatives. Today's exploration reveals a robotics field in rapid transformation, moving decisively from proof-of-concept demonstrations to practical, deployable systems that could fundamentally reshape how we work, live, and interact with technology. The convergence of efficiency improvements, enhanced capabilities, and robust safety measures suggests that many long-imagined robots are closer to reality than ever before. We're witnessing the foundation being laid for robots as true partners in creating a more capable, resilient, and intelligent world. Today's impossible breakthrough becomes tomorrow's everyday reality, and the robots are coming, not as human replacements, but as collaborative partners. This comprehensive analysis demonstrates how AI synthesis using Claude Sonnet 420250514 can process and synthesize complex research findings. The text-to-speech synthesis is powered by DeepRAM technology, while image generation utilizes OpenAI tools. Human expert review ensures accuracy throughout the process, though some oversights may exist. Full references are provided for verification. This methodology represents the cutting edge of AI-assisted research communication, enabling rapid synthesis of complex technical content into accessible formats, while maintaining scientific rigor and accuracy. Thank you for joining us on today's journey through the frontiers of robotics research. I encourage you to explore the full papers on the archive preprint server and connect with researchers sharing insights on social media. Share your thoughts using hashtag #AIFrontiers. Which breakthrough excited you most? What applications can you imagine? Your perspectives help shape future episodes. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses archive-preprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprintserver.org.